Hello everyone, my name is Ruru Xu and I'm from Istanbul Technical University. Today I'm going to talk about my work named Efficient MRI Reconstruction with Reinforcement Learning for Automatic Acquisition Stopping. MRI is safe, painless, and radiation-free, which is especially important for scanning and imaging internal organs and other soft tissues. However, MRI acquisition is slow, and subsampling is used to accelerate the MRI acquisition. This in turn reduces the image quality, and MRI reconstruction is needed to remove artifacts and obtain high-quality images. In the case of cardiac MRI, the heart movements make sampling more difficult, which requires longer scanning time, which is unbearable for patients. Cardiac MRI reconstruction. To improve the quality of reconstructed images, the most common method is to train a CA reconstruction network from a low-quality zero-field image to a high-quality reconstructed image. However, image domain-to-image domain reconstruction, like in unit-based networks, does not make full use of the information in the cascade frequency domain. Although the cascade-based network incorporates cascade information, they only use the fixed initialization under sampled cascades, and subsequent operations do not utilize the original cascade information. Optimized for cascade undersampling, reinforcement learning has emerged as a visible option to design optimal subsampling patterns like PTMR. But it requires manual intervention or fixed acceleration ratio to stop sampling. Does it automatically stop sampling? Can the acceleration ratio be determined automatically? We designed a policy network with a state single value. The output of the policy network is a vector containing L plus 1 values. L equals to 256 here. It corresponds to lines of frequency information in cascades. And the additional value is the state single value. We call the vector of the policy network output the probability distribution. And then, referring to the probability value, we are going to randomly sample a position as the next line to sample cascades. In the output section of the policy network, in each step, if the state single value is not selected, we mark it as false. That is, if one of the other 256 values is selected, we will sample a line at the corresponding position in cascades. During the training time, if the state single value is selected, we continue the reconstruction process. During the inference time, if the state single value is selected, we stop the entire reconstruction work. We also calculate the error between the reconstructed image and the fully sampled image. We added a penalty term to the reward. It consists of two parts. We will calculate the SSM error of the reconstructed image and the fully sampled image. And at the same time, we will calculate the error of the mask before and after reconstruction. Lambda is a hyperparameter to balance the penalty of new acquisitions with the reward of increased image quality. Lambda can be turned to choose between image quality and acquisition time automatically. Datasets. In our work, we used the OCMR datasets, which contains multi-coin cascade data. It includes 74 fully sampled cardiac datasets. We first convert the 4D information into the 3D information, and then we obtain 2D information data. We randomly divide it into training sets, validation sets, and testing sets. Reconstruction network process. The input to the network is zero-field images, which is the inverse Fourier transform of the undersampled cascades. The output of the network is a single channel of high-quality reconstructed images. Policy network process. We take the reconstructed image as the corresponding undersampled cascades as the initial state of the policy network. We conducted the experiment by setting the lambda to different values. Evaluation: we utilize SSIM and PSNR to show the trade-off between acquisition time and image quality. Validation of state single value. For each slice, the horizontal axis represents the step when sampling stops. The vertical axis represents the number of slices when sampling is stopped at this step. We can see that the smaller the value of lambda, the more critical it is for the acquisition steps. Higher values of lambda will generate faster acquisition automatically. We also compared our policy network with lambda equal to 0, which tend to stop at very late stages due to the lack of penalty for additional acquisitions. This further proves that the state single values work, and they can stop the Caspi's dynamic sampling process automatically. Automatically stop dynamic sampling analysis. The three curves in the label with the keyword not stop tend to be smooth, indicating that after the first selection of the state single, if the reconstruction of the slice is not stopped, most of the subsequent steps will continue to select the state single, so their mask is the same, and the slight increase in PCMR is due to the effect of the reconstruction network. Focusing on the three lines in the label with the stop keyword, we found that the smaller the value of lambda, the larger the average SSM, which also requires more steps. There is no significant smoothing of lambda equal to 0 because for most slices, the single vectors are first selected after step 96. In addition, we used the policy network to guide the sampling and random sampling of the next caspies respectively for comparison. We found that both SSM and PSL obtained by using the policy network were larger than those obtained by random sampling. Our conclusion is that our method can automatically stop sampling without losing too much SSM and PSIR, and a larger lambda value can cause the slice reconstruction process to stop early. Time analysis. We calculated the time spent in the cases of automatic dynamic stop sampling and 2 times acceleration sampling respectively. Compared with the fixed 2 times acceleration sampling, our automatic dynamic stop sampling method can save a lot of time, and the difference in acceleration time depends on the size of lambda value. Reconstructed image quality analysis. The comparative experimental result of our models and PGMR. When lambda equal to 0.0002, the acceleration of automatic stop sampling is 3.2. So we did an experiment on PGMR with the acceleration was 3.2. The SSM and PSL for both models were on pair. Similarly, when lambda equal to 0.0005, the acceleration with the reconstruction process is stopped automatically at 5.95. We conducted experiments on PGMR when acceleration of caspids under sampling was 5.95. By comparison, their SSM and PSNR, we also found that they were very similar. In summary, compared with PGMR, our method has no loss of accuracy, and it can automatically stop dynamic sampling. We propose a sampling policy based on reinforcement learning for caspids that can apply different sampling schemes for different slices and automatically stop when a satisfactory image quality is reached. We designed a novel reward which penalizes the acquisitions of new caspids lines and encourages improved image quality. We validate the subsampling strategy using caspid undersampling on cardiac MRI for the first time in the literature to the best of our knowledge. The experimental results show that the compatibility of our method to balance the trade-off between acquisition time and image quality automatically. In future, we aim to design specific reward functions for downstream tasks to optimize the subsampling and stopping criteria. Thank you for your attention.